Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Hello, Senior 6 Chemistry students. How are you? Welcome back. Alan is my name, still with you in the chemistry lessons. As I had told you in the previous lesson, we are still on the chemical kinetics, which is the second last in our topics, and looking at unit 14, which is about rate laws and their measurements. So in this lesson, we are going to be looking at measuring the rates of reaction. Just a quick recap. In unit 13, we are looking at the factors that affect the rates of reaction, where we talked of concentration, pressure, light intensity, change in temperature, and so on. So after seeing how the reaction actually occurs and those factors, we need to go ahead and determine or measure the rates of reaction. And that is what is the content for today's lesson. As I had said, the focus in today's lesson will be on the measurable physical quantities which relate to the rates of reaction, or the physical quantities that we base on in determining the rate of a reaction. Then we see how to obtain instantaneous and the average rates of a reaction. So that is what will be making up today's content. And as such, the crucial, or what we call key terms in our lesson, are instantaneous rate of reaction and average rate of reaction, as you see here. So what are they? What is instantaneous rate and what is the average rate? I think the word average isn't new to you. Maybe instantaneous just implies at that specific time, at that time point, what would be the rate of a reaction if you're following up the reaction and how it is occurring. So that is what we shall look at, and from the content to be covered, we have two objectives. One is you're supposed to plot correctly experimental data on the graph and use the graph to determine instantaneous and average rates. Of course, in this case, the data you're going to use is the data already obtained, because you understand the situation we are in. We can't get all of you to go into the lab and carry out the experimentation, but we shall have the data already from the experiments done, then we work on them. So those are the two objectives that we shall go through, or we shall aim at achieving. Now let's go to today's content, reaction rates. I think those structures or those images aren't new to you. It's part of what we looked at in Unit 13 about the speeds of a reaction. And as you already know, for instance, this roll of barbed wire, with time, if it is left exposed in the atmosphere, it will rust. So we have the rusting in here. And majority of us like taking part in parties or going to parties, birthday parties, weddings, introduction, or end-of-year parties. We normally light fireworks as a way of climaxing the celebration. So you notice when you use a matchbox and you put it on the fireworks stick, in a blink of an eye, there will be an explosion, or there will be this light coming out. So this is part, we call it combustion, then here we have rusting. You will come to notice that these two reactions actually occur at different speeds, or in this case, at different rates. Like rusting, it will require months and months, sometimes even years, for it to occur, but this lighting up a firework stick will just take a blink of an eye, a few seconds, and that takes us to look back on the fast reactions and the slow reactions, giving the examples, fermentation, rusting, and much of the organic. So the point we are looking at is, in reality, reactions will always have different rates. So the question we have is, how can we quantitatively determine rates of reaction for different reactions? Is it possible to determine the rate of a reaction, for instance, the rate at which rusting occurs? Yes, it is possible. Or the rate at which the time it takes for this firework stick to produce the sparks? Yes, it is possible. So now the question, if it is possible, how? And that is what we shall be looking at in details, and see how to come up with the value, quantitative figure on the rates of reaction. Measuring rates of reaction. Let's start with what we already know. Of course, we already know that rate is synonymous to speed in this case. So how do we determine the speed of a moving car? Look at the slide. That's the car. It's accelerating steadily on the road. How is the speed of this car determined? This is part of what you normally cover in your elementary science, in the ordinary science. Basically, speed of the moving car would be the distance covered and in the time range. For instance, the time can be in hours or sometimes in seconds, depending on the unit you want to use. So the speed would be the distance in kilometers per unit time, as I said, hours or seconds. Similarly, can we now transfer this understanding to the speeds of reaction or the rates of reaction? In a chemical reaction, the rate of a reaction will be a physical change, any measurable physical change with time. Time, of course, this is whether you want to call it seconds or hours, but mostly we use seconds. Now, the other part would be, what do you mean by physical change? What are those measurable physical changes or measurable physical quantities? When we are looking at rates of chemical reactions, there are a lot of measurable changes that one can follow, but the prominent ones are change in mass before and after a reaction, or change in mass as the reaction is occurring. You can look at the products, for instance, the volume of the gas produced per unit time. You can look at other factors or other quantities like change in pH. That would be for the case of acid-base reactions. You can follow the change in pH and know what is happening. For instance, if you add a base to an acid, but the best way in chemistry it is the acid to a base, so the pH will be changing from basic, which is around 14 or 13, and it is dropping down, it is lowering. So in that way, you can tell that the reaction is actually occurring. Are there other measurable physical aspects or quantities that you would follow? Look even at the electrical properties. Change in conductivity, the conductance of a solution, indicating, depending on the ions present in solution, if they are being removed, then the conductivity is changing. In that way, you can notice that the reaction is occurring. And the color change. Much of the time, we normally look at the colors to tell us if the reaction has occurred or it is still occurring. So those are the measurable changes that one would opt for when you're looking at a rate of reaction. The point here is rate of reaction is any physical change detected or measured within time range. It can tell you how the reaction is going. Now, let's take a few examples and look at how, for instance, mass can be based on in determining the rate of a reaction. Mass loss method. We are going to use the example of calcium carbonate reacting with hydrochloric acid giving carbon dioxide gas. You notice in here, to form carbon dioxide gas, the carbonate must disintegrate, or it must react, or it must be used up. So following up the changes in the mass of this solid as gas is escaping, then we can determine the rate of a reaction. So how would we carry out such a kind of experimentation? Simple. Take a look at the illustration. Take a close look at that illustration. We have our marble chips, which is calcium carbonate. When you react it with the acid, hydrochloric acid, the gas carbon dioxide will fume out, will come out. So you need to seal up the container with a cotton wool to prevent maybe other fumes other than the carbon dioxide coming out, because in that way you will be maintaining, you'll be controlling that experiment. So if you brought this container just immediately after mixing up the components and you weigh the container at the start, then you always take notice on the changes in the weight of this container as the reaction is happening. What will happen? You will notice that the mass is decreasing because the gas is coming out and the gas is taking some part of the mass of these reactants. And so the end product you'll end up having result of that category. That is typical following the minute per minute change in the mass, or following second per second change in the mass. Of course, this is about the timing you set. What do you see with the typical result? What do you see? What do you observe from that curve directly? You notice that it is sloping downwards, or it has a negative slope. What does that imply? The mass of the reactant, which is calcium carbonate, is decreasing since it is being lost in form of carbon dioxide gas, as you see the illustration right there. So the mass will be decreasing. So in this case, the mass curve, it has a negative slope. Of course, that is when you plot the mass of the flask with time. So one other aspect you need to look at is the initial rate. At least at the start, you see it is very steep. So this steep part is what gives us the initial speed of a reaction. So if you followed up the curve, then you can find the rate of reaction at any moment during the reaction. So basically, that is a setup one would opt for when you're determining the rate of reaction in regard to mass loss. Let's look at another physical quantity, then we make a comparison. The changes in the volume of gas produced. So in this case, we can follow the gas as a product. The other was the mass of the reactant. This is now the volume of the gas as a product. Let's use another example. Zinc reacting with HCl to form hydrogen gas. From your understanding, this being a gas, we need like a syringe. So you would have a setup of this category. That is the setup of the experiment you would carry out, whereby this is a stop clock. You set the time range Maybe you can be timing every 30 seconds or every 15 seconds or every an hour, depending on the reaction you're carrying out. So if you mix up zinc and the HCl, the reaction will occur. So if you time up at the start of the reaction, the amount of the gas being released, you get it from the gas syringe. With time, you can get accumulated data. And so you can also plot it looking at the volume of the gas and time it has taken to accumulate that amount of the gas. So you would end up having a curve of this category. What do you notice? Take a minute, look at this curve, relate it with the previous curve that we looked at. Relate it with this curve. What do you notice? This is having a negative slope. This is having a positive slope. In other words, it is increasing. So from this, you directly notice that for products, they increase as reactants decrease. That is an immediate observation you would get. So also, again, you see the reaction is faster at the start. It tends to slow down and even tends to become constant as time goes on. Of course, we shall let alone look at the reasons behind that in our few slides. But this is now a typical result that you would get if you follow a product like the gas or like the concentration of zinc chloride. On the other hand, it would also show such a kind of a graph. So with those two categories, you can see you can determine the rate on how it is going. The question now is exactly, after I've gotten these values, how do I get a numerical value related to such a curve to know that the rate that is happening is like 1, for instance, the volume of a gas will be like 1 cubic centimeters per second or like 2 cubic centimeters per second. How do we come up with the quantitative value? So that is possible if we sum up all this and the whole aspect is summed up in terms of concentration. So the rate of reaction and concentration, instead of using mass alone, volume alone, and those other physical quantities, we look at the whole component of the reactants, and it is best described in terms of the concentrations. So the rate of a reaction is basically the change in the concentration of either one of reactants or products with time. Suppose we have that reaction, you have A, B giving C, D. This is a general. We've already looked at some of the examples of the reactions before, like for zinc and HCl or calcium carbonate and HCl giving different products. So here we are giving a general sum. From this general sum, we can get the general methods to apply in getting that quantitative number relating to the rate of a reaction. Like as we had already seen, for the products, they increase. So you would look at the rate in terms of increase in the concentration with time changing. For reactants, they decrease, and you would basically find this is the general curve for rates of reaction in regard to concentration. Products increase, reactants decrease. So a few points we need to understand. I remember I promised you we shall explain these curves. What you need to know is for products, they have a positive slope. This is what we mean. If you calculate slope for this curve, it will be a positive value. For reactants, it's a negative value. And negative means the concentration of reactants are reducing in amounts, whereas the concentration of products are increasing in amounts. That is understandable. You're taking from here and add it in here. Reactants, products. One other thing, the rate is normally greatest at the start because we have the maximum amount of reacting molecules possible at the start of a reaction. And it reduces as the reaction occurs, tending to equilibrium. Such a point is where we may have the equilibrium position in there. Of course, you already have the understanding of equilibrium from our chemical equilibrium lessons in previous units. So the reason for that slowing is as the reaction is occurring, the concentration of molecules is reducing. And when it reduces, of course, the effective collisions will be reducing. And so the reaction slows down. Then at the end, normally we have the slope tending to 0 because that is where we have the reaction almost ceasing to happen, or it is stopping. Now, how do we get the quantitative values? Remember I told you of that. And this takes us to instantaneous and the average rates. Instantaneous, the rate or the speed at that point when the reaction is occurring, at a specific point when the reaction is occurring. So from the whole methods we've seen, if you have a graph using the data that you've obtained from the experimentation, you can get the rates. Average rate basically is just the total changes that have occurred over total time taken. Whereas instantaneous rate, which is the rate at a given time, you look at the gradient or the slope of that component. Let's use this example to make it much more understandable. We are going to follow up the volume of hydrogen gas produced in the zinc and HCl reaction and come up with the values for the average rate and instantaneous rate, or what we call the rate at a given time. So, again, this is a typical curve for hydrogen gas produced. You see, if you plotted it, plotting the values or the experimental data, you would get it this way. So the average rate would be the total changes, as you see. All this, the total changes over total time, from here to here, or from this point and up to 0. This gives us the total changes. Then this gives us the total time under that experimentation. When you substitute them, then you get directly the average rate for that reaction. So how do we get instantaneous rate? Let's take an example, instantaneous rate at 90 seconds, if you're still using that illustration. So you would have to draw a line from that time, 90 seconds, extrapolate it up to when it meets the curve. So when it meets the curve, then you find the tangent, or you find the slope at that point, which will be the change in the y, or in this case, the volume of hydrogen gas, and the change in the time. Then you will get the instantaneous rate, or the rate at that given time. Does that make it clear? The curve is well illustrating what is happening. So now you understand how to get the instantaneous rate and the average rate. Average, the total changes over time. Instantaneous, you look at that point, then you find the slope. So, of course, this comes after you've plotted a graph. So, that is it with the instantaneous and the average rates relative to how you determine the rates of reaction. If we can do a recap very fast, the rate of a reaction is you look at the changes in the physical quantities. You can look at the mass, the gas produced, or the changes in the pH, and so on, with time. If you follow up how that change is happening as time passes on, then you will get a table of results which you can plot, and from them you can get directly the rates of reactions. Now, of course, I can't live without giving you the exercise. This exercise is a whole complete sum up of what we've gone through. If you can critically go through all those numbers, trust me, you will have understood the instantaneous rate of reaction and the average rate of reaction. So this exercise still is about the reaction of zinc and hydrochloric acid, whereby the production of hydrogen gas was recorded every 30 seconds for the duration of 10 minutes. So you have 0 to 300 seconds, and this is the volume. So you will meet a few questions. They are really almost similar but totally different. Like this says, determine the average rate for the reaction. Part C, determine the average rate for the reaction in the first 90 seconds. This is for the whole experimentation time. This is for 90 seconds. Determine the rate of reaction at 60 seconds and 210 seconds. So in this part, D is about instantaneous rates. This is about the average rates. Then compare the rates at 60 and 210 seconds and give a reason for your answer. Finally, predict with a reason why there will be, if there is any more hydrogen produced beyond 300 seconds after it has expired. So, such a kind of a question will help you to understand what you've gone through and practically, and physically do the calculation by yourself for you to understand the concept. Thank you for being part of the lesson. I'm glad that you're still with me. You stay safe, follow the Ministry of Health regulations. I want to see you in the next lesson. Bye.